Okay. All right. Cursor is showing up on my screen too, or no?
I don't see a cursor.
That's okay, but you can see me right, probably.
Yes, yeah.
Okay, good.
Yeah, and whenever you're ready, it seems like a bunch of people have showed up already. So,
Okay.
Yeah, so we're happy to have Nima here and talk about his recent work. Yeah, I guess just take it away.
All right, thanks, Jonah. Thanks for coming. Thanks for coming to listen to me talk about this work we did. So I'm gonna talk today about some work I did with Henry Cohen, Tom Hartman, and Amir Tajdini. I should also mention work by Maloney and Witten that appeared on the same day. They had similar ideas and they went about it in a slightly different way. So I don't know about you guys, but I haven't seen an actual chalkboard in months. So I'm gonna try to give this talk as though it's a Blackboard talk and see how that goes, which will allow me to slow down or speed up if you guys give me feedback to say this is too basic or it's too fast. And I should say there's no, I don't have an agenda. We can get as far as we get. If there's more questions, I'll be happy to slow down and talk about things. So that is to say, at any point, feel free to stop me and ask questions. Okay, so this is a rough plan of my talk, and if there is no questions about it, I'll just go ahead and get started. So, the title of the talk is 3D gravity from averaging 2D CFTs. But the first question one might ask is why might you want to try to get gravity from averaging CFTs? And I will try to give a few motivating remarks, quantum theories, why you might try to find a manifestation of gravity emerging from some ensemble average in CFTs. Well, the first motivation that I'll give and a review is that of pure 3D gravity. And by pure 3D gravity in this context, I mean some pure 3D gravity in ADS that's dual to some CFT. What I would mean by gravity is something that has the vacuum ADS as a solution, and it also has gravitons, the boundary gravitons, as a solution. And this thing would be dual to the CFT vacuum, and the Virasoro modes would play the role of the boundary gravitons. In addition, if it's a pure theory of gravity, you would expect to include the other saddles, namely the BTZ black hole. And these things would be dual on the CFT side to the so-called heavy states. That is, states whose scaling dimensions scales with C, as you take C to be large, so that you can get a semi-classical gravity. Along these lines, so this might be the simplest theory of gravity you might imagine. So it just has gravity, its saddles, and its excitations without any additional matter. There was attempts to construct such a CFT by Maloney and Witten back in 2007 by Maloney and Witten. By the way, is my screen legible? Am I writing big enough and stuff?
Looks good.
Looks good. Okay, good. So there was an attempt to construct this by performing a path integral, a gravitational path integral, and summing over some saddles of their choosing. And the partition function, let's see if this works. Good. Is this thing here, where the path integral ZMW is given by some integral over geometries. And you can explicitly express this as a sum on, as a what's known as a Poincare sum, which is you take the vacuum Virasoro character and you sum over its images to construct something that is modular invariant. So by construction, this object is modular invariant. Oops. Yeah, by construction, this object is modular invariant, but it has other issues. So it has other issues in the sense that this is not a sensible CFT when you try to interpret this partition function that I wrote, the torus partition function, when you try to interpret it as some trace over some Hilbert space, so trace e to the minus beta h. One of the issues it has is that it's got a continuous spectrum of operators, which is not something you would expect out of a compact field theory. Another more serious problem that it has is that it has negative degeneracies, which is a much more serious issue. So you might say, well, maybe you can try to fix this by, include other saddles, maybe. You could say, maybe I'll try to fix this by including some minimal matter to try to fix the negative degeneracies. And there's been various works along this direction, these directions by various authors, which I will try to, oops. This is not working as well as I thought. So there's been work along these directions. For example, this work of Maxwell and Teriachi had motivated by JT gravity, included some other saddles, which they claim fixes the negative issue and so on. But the continuous spectrum is not so easy to fix. However, one might imagine that if
Nima, can you explain a bit what negative degeneracy means?
Negative degeneracy means if you try to write this as a Q expansion, which is tracing over the representations of Virasoro, the coefficients that appear in a unitary CFT count the number of states. But when you take this explicit expression that they have here and try to expand it, you'll get a negative number of states. Or, yeah.
Okay, thanks. And changing these coefficients breaks modular invariance, I guess.
No, it doesn't break modular invariance.
Let's say if you wanted to just make them positive or something, that would break modular invariance.
Yeah, I mean, you can't arbitrarily
just change things. Okay, good. Thanks.
And Nima, is there some expectation from the gravity point of view that the dual CFT should be compact rather than non-compact?
A priori, I guess not.
I mean, there's nothing wrong with a non-compact CFT.
I agree. So yeah, I don't really see this continuous set of states as a problem necessarily. I don't have a first principles argument as to why this should be happening. You should be getting a continuous spectrum.
If you want to interpret this as a theory of gravity and the thing that you're counting as black hole microstates, I think you want the spectrum to be discrete with a gap.
Even above the BTZ threshold?
Yes.
You're saying this because you would say that you're gonna get higher entropies than you would expect from BTZ black holes in gravity.
Yeah, you have to say that what the partition function is telling you about is some kind of density of states in a continuum, rather than saying that you just have some discrete states that you count. So the interpretation of the entropy would have to be something other than counting states.
Yeah, that's fair enough. Although a priori, I don't see that being in like different words you associate to the word entropy. I don't see that being in contradiction and with anything I hold dear in quantum gravity.
I thought in the D1, D5 moduli space, isn't there a point where you get a continuous spectrum with a gap?
So there's a continuous spectrum above a gap, but that comes because there's a you have that happens because the system is neutrally stable to fragmenting once you exceed the gap. So
this thing also has a gap, by the way.
Yeah. There's a gap because the system can fragment into two pieces above some energy threshold. So in particular, I mean, this is the kind of thing that David's been studying for years, where you can pull strings or fibranes out of the system. So so there it's okay, and you understand what it is. The continuous spectrum is simply that you can fragment the system into two pieces, and those two pieces can have arbitrary relative momentum. But
that's in flat space, right?
No. This is an ADS3. It's that the it's that for codimension 4 subset of the moduli space, if you want to say, like, take a string out of the system in the 1 brane, 5 brane bound states, that the energy that it costs you to stretch the string as you try to pull it out to the ADS boundary is compensated by an equal and opposite force from the H flux. And that's very special to ADS3.
Okay.
Okay, well, I mean, I'm gonna try to suggest another possible reason as to why there's a continuous spectrum. That is to say, if this was dual to some compact CFT with discrete spectra and you averaged over it, you would obtain a continuous density of states in this dual theory.
Right.
I am not going to give an example of that for pure gravity. I will give it for some other situation where this does happen. And but I don't really have I don't really have some UV complete way of describing this in the sense that you described, where there is some momentum that accounts for the continuous density of states.
I always thought that this was just because gravity isn't smart enough to understand what the microstate structure is.
That's possible, and you would need, yeah, maybe you need some UV. You really need the full UV thing to, yeah.
Yeah, I mean, it's just a statement that gravity can't resolve down to energy differences of order e to the minus s. So it just treats it as a continuum.
Yeah, but that's sort of like taking an effective field theory approach, whereas here I'm saying, well, let me sum over all possible non-perturbative saddles of this gravity in ADS and get some partition function that has got all these other non-perturbative things. You're saying, well, maybe that's the same in logic anyways.
Yeah, well, yeah, gravity, I mean, it's the same spirit as Gibbons-Hawking, right? So Gibbons-Hawking, you evaluate the Euclidean action of the gravity theory, and it gives you an entropy count.
Yeah, but you don't include the other non-perturbative saddles in that case. You just include the single black hole, whereas here I'm summing over all possible.
Yeah, that's an elaboration. So for instance, when Atish-Dabelkar, counts some spectrum of ADS2 black holes, he sums over different saddles. So, there, because it's BPS and everything, you actually get, a discrete spectrum of integers after you, do some very fancy mathematical physics. But that hasn't yet appeared from this sort of a construction.
Fair enough. I mean, yeah, okay. I don't really have too much to say about it, except that there are ways of including matter that makes this a perhaps well-defined unitary CFT with a continuous spectrum. Now, I'm not sure whether I should say the same words again, that like, you know, gravity and minimal matter isn't smart enough to know about the microstates. That's certainly sensible. And I mean, this isn't really a top-down construction. This is just, you write down this silly thing, you sum over images, and then you try to fix it up by engineering. So,
I mean, in part, it's because, I mean, there kind of aren't enough degrees of freedom in the theory. Like in the things that Maloney and Witten were doing, basically, as you say, it's just the boundary gravitons.
Yeah.
There's nothing other than some kind of asymptotic deformations.
Well, there's infinitely many of them, but yeah.
There are infinitely many of them, but there's sort of like C of order 1 rather than C of order C.
Right. Yeah.
I mean, the 2D version of the 2D counterpart of this, I mean, so if you're saying, let's go to two-dimensional CFT rather than three-dimensional gravity, Liouville theory is kind of like the universal theory of Virasoro ward identities. And if you ask, what's the partition function of Liouville theory, it has a continuous spectrum above a gap, but all there is
gap there.
One scalar field worth of degrees of freedom.
Right.
Not, you know, you can make any central charge you want, but if you ask, what is the partition function counting? It's counting a continuous spectrum of 0 modes plus 1 tower of oscillators. And, so, Liouville theory doesn't have, even though the central charge is enormous, when you actually ask, what do you get when you look at the asymptotics of the Carty formula, it's, a C effective of order 1. And my sense is that these 3D gravity constructions is sort of like the 3D analog of Liouville in 2D.
Except the Carty formula here is exponential.
Some universal identity sector of global gravitons, and you can count those, but you really have no idea how to get e to the c actual states in the asymptotic spectrum.
The Carty formula applied to this is exponential. I mean, it has the vacuum, right? The reason you don't get that in Liouville is because Liouville doesn't have the vacuum. Here, if you try to apply Carty, and the fact that you're reproducing the vacuum tells you that you have to have exponential number of states asymptotically. I mean, I agree, but whether or not there exists a theory which has just gravity, its saddles, and some minimal matter corresponding to real theory of gravity is not obviously ruled out to me, other than saying that, well, I don't have a string theory construction of this, because it seems to satisfy everything else. And in any case, that's not really the direction I'm going.
Defer this discussion till later.
All right. Okay. Okay. So maybe we can discuss that afterwards if you like. Yeah. The words I was going to associate with the continuous spectrum is that, like, maybe this comes from averaging. So that's one possible motivation. The other motivation I was going to mention is these recent works of the so-called pure gravity in 2D, which is some JT gravity, some Jackie Teitelbaum gravity theory, which is dual to random matrix theory. There's these beautiful works starting with Saad Shankar, Stanford, and then Witten, Stanford, and various other people who've expanded this duality. The features that this thing has in common with what I was saying before is that this comes from some ensemble average. And on top of that, it also has continuous spectra. So it fits this mold of what I was trying to describe before. One other possible motivation, which I find maybe slightly more convincing, is the so-called factorization problem. So factorization problem, very crudely put, is if you have disconnected boundaries with quantum field theories living on them, and you compute the partition function, what you will get is a product of disconnected partition functions. But if you try to include gravity, you have disconnected gravity ways of filling the boundaries in, but you also have the so-called space-time wormholes that fill in the geometry. So the answer that you're getting isn't just the factorized partition functions, which is what I would expect from the QFT calculation. So one possible way you could have the boundaries talk to each other is if you do some sort of averaging. So that's one possible other motivation. I think this story is older than Maldacena knows, but a good place to where they explicitly mention it is in this paper about Maldacena.
Are these wormholes not allowed in, like, is there some reason why we don't have them in dualities where it's like a single dual theory and definitely not in ensembles, like n equals 4? Like
n equals 4 super-Yang-Mills?
Like, are you not allowed to connect in the, is there something that tells us we're not allowed to do this?
If you do effective field theory, I think they are there. So one of two things must happen. Either they cancel and those solutions won't contribute, or something else. And I don't know what that something else is.
I mean, it's a non-perturbative effect, right? It can be compensated for by other non-perturbative effects. That
yeah. So in principle, there could be other saddles that resum and cancel this one.
Okay, so it would be allowed in gravity, or there's no a priori reason not to allow it.
Yeah, if you just write down the effective
cancellation.
Yeah. Generically,
it's not a completely obvious. It's not known what actually happens. That's why it's a problem.
Yeah, especially in a theory like that, it's not known. But what I'm saying is, if you just write down the effective field theory, like the supergravity dual to n equals 4, I think generically you have these saddles.
Yes, I agree with that. There's a solution.
Okay.
Right. But they're explicitly absent in the CFT, right? That
they're explicitly absent in the CFT. That's correct. You just have the factorized partition function.
You just have tensor product of CFTs, yeah.
That's correct.
Nima?
Yes.
Is it obvious what happens in Chern-Simons theory? Like, say U1 level K Chern-Simons theory.
So you have two disconnected boundaries that are dual to U1 Chern-Simons, and you're asking, should I include Chern-Simon saddles that make these two boundaries talk to each other?
Yeah, right. So I mean, say you turn on like a boundary Wilson line on one of the boundaries, that should source flux into the bulk, and you can say maybe it flows out to the other boundary.
I'm going to claim that it should flow out. I mean, in one particular example that I will give, which will be dual to something like a Chern-Simons theory, I claim that, well, if you average over it, those things contribute. I'm not sure what'll happen if it's just a dual CFTs. It's like what Emil said. There's no way for them to talk to each other. There should be just a factorized CFTs. The question is whether if you try to do the calculation in the Chern-Simons directly, should you include configurations that connect the two boundaries? One reason I would say maybe you should include them is because they give more sensible answers to some calculations we can do, for example, in the context of the time and entropy of evaporating black holes and so on, but that might not be a very strong argument.
I guess I don't understand the premise. So we're talking about doing Chern-Simons theory. You have to say what manifold you're doing it on. So, I mean, the manifold may have disconnected boundary components, but you have to specify what manifold before you even begin.
Right, I guess I was taking as part of the description of the theory as sum over all possible manifolds with that, which is what I would expect to do in gravity, but not in Chern-Simons. That's the spirit in which I was taking it. Okay. Is there any other questions? If not, yeah, yes.
In the SYK case, currently believe that the correct picture is that in the bulk you have a single gravity theory, but on the boundary you have to do some average over different quantum systems.
Yeah.
Is that the current belief if that's what's correct?
Sorry, I didn't hear the last thing you said. You were cutting out.
Oh, is that what's currently believed to be the correct picture?
Believed.
Of this duality?
I mean, yeah, the one that I'll also give an example of today have the same flavor. So the boundary thing you ensemble average over, and it's dual to a single theory of gravity on the bulk. And believed to be correct, I'm not sure. Depends who you ask, I guess, and in what context. Yeah. Okay, just maybe one other motivation for why is you might expect some emergent gravity out of averaging is because in some sense we're used to averaging giving rise to semi-classical gravity. This is different in spirit because you're averaging over the same theory. It's sort of related to what Nima was saying of like, if I take heavy states in a CFT, in a holographic CFT, and I take some window and average over these states, the dual description that I get of this is the semi-classical black hole geometry. So this kind of averaging is something that we're used to. So it's possible that you might expect some semi-classical description emerging out of some averaging procedure, which maybe is nothing more than just simplifying the calculation for explicit instantiation of a theory, which is another perspective you can take. And then there's a bunch of other things, but let me just move on from motivation. Okay, so let me make the claim, perhaps this pure gravity in 3D, in the sense I described above, is dual to some averaged theory in the boundary. But as soon as you make this statement, you have to be much more specific in what it is that you're talking about. So when you say the word average, what do you mean? Average with what measure? What measure? And on top of that, you also have to tell me what are you averaging over? So average over what? Which theories? There's lots of CFTs. Maybe what you're supposed to do is you're supposed to average over all CFT data subject to some constraint or something. Well, I don't really know how to do that because the bootstrap problem in 2D CFTs isn't solved yet, so this is difficult. Maybe you're supposed to average over some conformal manifold. But the pure gravity that I described above doesn't actually have marginal deformation. So again, this is a difficult problem, which I don't know how to answer. So instead, what I'll do is I will step back and do something simpler. So step back and consider the simplest thing. Consider the simplest thing possible. And the simplest thing I know of in 2D is just a bunch of free bosons. So I will take, say I'll take C free bosons, free compact bosons in 2D. These things are simple because they have a large symmetry group. They have a U1 to the C times U1 to the C current algebra. In addition, they have the added bonus that they are exactly solvable, given that they're free, so that's helpful. In addition, they have an exactly known moduli space. So that gives me a sense for averaging. So it tells me what I'm going to average over. So it seems like it has all the ingredients I would need, at least in some toy example, to carry out this program explicitly. And I make the following claim, and let's see how far we get. I claim that averaging these CFTs is dual to some theory of gravity, which I'll describe below. And I will verify this at least in the case of a torus boundary. So I'll verify this case.
Nima, I thought in your paper, or maybe in Maloney-Witten, that for C equals 1, this doesn't work.
That's true. You actually, so I would talk about this in a bit, but it actually, what you need is that you need C to be greater than, well, let's see, I need C greater than genus plus 1. So this, Maloney and Witten actually showed that this type of thing holds on things with multiple holes, so higher genus things. And the claim is that the duality that I described works as long as C is greater than G plus 1.
So this is, the gravity dual is on a space that is asymptotic to this, whose boundary is this genus G surface?
That's right. So in the case of the torus, that plus a sum on different ways of filling it in.
Right, okay.
Yeah.
How are we supposed to interpret the fact that there's no finite but large C version of this that works on all genus?
Well, I was going to talk about that too. You can, okay. Well, there's a couple different ways of interpreting this. One is to say, well, this theory is not well defined because it's not defined on arbitrary genuses. Another possibility is that doubly non-perturbative contributions could resum to fix it, because in some sense the C here in the bulk dual is like H bar. It's the thing that appears in front of the action. So you could imagine we're just computing the leading term, but you're supposed to include all other contributions that could potentially regulate these divergent contributions, that when you sum them up, you get some sensible answer. And I'm not sure which one is the correct answer.
But I have a question.
Yes.
So if when you're averaging all these different like bosonic theories, would the evolution of a state won't be unitary, right?
Sorry, the evolution, can you say
if
again,
you
please?
pick a state in the CFT, the evolution won't be unitary because you're averaging all different things. Like at least it's not guaranteed, right?
Yeah, it's not, the averaging is not, I mean, yeah, you're averaging over unitary CFTs, that's correct, yeah.
But the whole evolution won't be unitary.
The whole evolution will be the evolution of unitary CFTs that you average over afterwards. I mean, it's not gonna have unitarity in the sense that you would think, but there is still some essence of unitarity left. So for example, you're going to have unitary spectra still, because you're averaging a bunch of unitary spectra. So you can't find something that's not unitary in that sense.
But Nima, it is true that the unitarity constraints of an averaged family are different than a single instance of a unitary theory, right?
That's correct, but you're still not going to get negative degeneration.
I get that, but I wonder actually if do we understand those differences well enough to prove, for instance, that 3D pure gravity has to be an averaged theory? Has to be dual to an average theory, that it can't be a single instance?
Well, there is a claim by Gliozzi that came out a couple of days ago, who
I saw that, but
like
that's
that.
A different.
Right, it's not.
First of all, I think that argument is wrong. But second of all, that's a very different.
Right, it's not. I agree. It's not imposing the average unitary constraints. I agree. I'm not sure if I haven't really thought about it. It might be possible. That's interesting.
Yeah, let's talk about it more.
Okay.
But anyway, just to sidebar, I think that that Gliazzi paper is probably wrong because it's not. It looks like the argument would work for a continuous spectrum also.
Ah.
So the old nemesis that we were just discussing before.
Okay.
So anyway.
I see. Okay. Yeah, we should talk about that too. Okay. So now, even though I just said that C equals 1 doesn't work, it's still instructive to maybe talk about it as like very quickly. Free compact boson. It's C equals 1, just so we can orient ourselves. Maybe this is already fresh in everybody's mind, but I'll just be quick. So you can write down an action for a free compact boson where you compactify, so you identify the sigma, the field with itself up to some scaling. This thing has U1 times U1 symmetry, which realizes the shift symmetry. So this action has only got derivative, so it's got shift symmetry. There exists a marginal operator, dx d bar x, which just, if you exponentiate this and stick it in the action, it generates the change in the moduli. So the moduli for me here is just a radius. And anytime you have a CFT with marginal operators, you naturally have a metric and this moduli space, which you can obtain by just computing the Zamolodchikov metric, which is essentially, if I take this thing to be O, by computing the 2-point function of the marginal operators, you get some metric. And in this particular case, it's simple enough to write it down. Let me just write it down. It's just R squared, dr squared over R squared. So that's the metric on the moduli space. In this case, the theory is simple enough that we also know the torus partition function. And if this was working properly, it's this. I'm writing it down explicitly. The form of it is not super important. I'm only writing it down just so that you can observe that it's invariant under R goes to 2 over R, the ordinary T-duality group that we're used to. So that tells me that the moduli space isn't all possible radii. The moduli space in this particular case is R from 1 to infinity. Is there any questions about that? Okay, good. This is just quick review. Now let's talk about, oops.
Shouldn't it be square root of 2 to infinity?
Maybe, yeah. I don't know if I chose that normalization. No, I think it might.
No, I mean the range of R, because when you put the 2 there, the fixed point is R equals root 2.
That's probably correct. Yeah. Yeah, that's correct. So I just wanted to mention this because it'll also appear when I talk about multiple free bosons. You'll have to worry about that T-duality group. Okay, now let's talk about C free bosons. Again, you can write down a sigma model. There exists some nonlinear sigma model you can write down. It's parametrized by a flux and a metric instead of just a radius. But I'm not going to go that route. Instead, what I'm gonna say is I'm gonna talk about the construction of Narain from a long time ago, which said that essentially you compactify a bunch of bosons. You essentially identify them with themselves up to some lattice. And what Narain said is that you can directly construct, for example, the partition function only speaking about the lattice. So let's talk about the Narain construction. So there is something called the Narain lattice, which is, it's consisted of the points which I will label by vectors x and y, which live in Lorentzian space with signature C comma C. It's a 2C dimensional space. And I claim that if I can find it somewhere, yeah, it's here. Let me just write down the partition function and let's talk about it. I was hoping that this would be more helpful, but so here's the given a lattice with points x and y, you can write the partition function on a torus as a sum over states where these d's are counting the number of states, these chi's are the characters of the u1 to the c times u1 to the c algebra. They're simply q to the h over eta dedicand eta to the c. And you can, in terms of the lattice, you can rewrite it as a sum over, is this visible? Maybe I should make it a little bigger. It's a sum over the points that are in the lattice with q and q bar to the norm of the c-dimensional subspaces individually. And just for future reference, let me just highlight this form of it, which is just rewriting it in terms of some integral over some density of states at each spin L. Now, what I wanted to say about this lattice is that it's not any arbitrary lattice will go. So the partition function should have modular invariance. So this thing is generated by T transformations, which tells you that spins are integers, which forces the lattice lambda to be an even lattice, meaning that the natural inner product x squared minus y squared needs to be an even integer. In addition, it also needs to satisfy S transformation invariance. So this tells you that, I will not show this, but it just tells you that lambda has to be self-dual, meaning that the volume of the fundamental domain is equal to the volume of the dual, the inverse dual. So the thing that I want you to remember is just that points in lambda, points in the lattice label my quantum states, label my states. And the exact labeling is as follows. So delta, the scaling dimension is 1/2 x squared plus y squared, and L is 1/2 x squared minus y squared. Okay. Now, now we want to. Okay, is there any questions about this construction? If not, I'm gonna start talking about how to average over these CFTs. So the claim that I make is that these CFTs, instead of being parametrized by the flux and the metric in terms of the nonlinear sigma model, can also be parametrized by the Narain lattice itself. So averaging over CFT is like averaging over the Narain lattice. The question is, what is the moduli space of Narain lattice? What is the moduli space? And I claim the following. Given a particular Narain lattice, lambda naught, can generate all other lattices by the action of O, C, comma, C, R. remember OC comma CR preserves the integrality of spins, and I claim that this generates other Narain lattices. And but if you remember the expression for delta and L, quickly looking at it, you'll notice that not all OC comma C transformations generate a new lattice. Namely, OC, the ones that can be written as OC times OC will not change the spectrum, which will not give you a new lattice. And on top of that, there's the analog of the T-duality group, which will not give you new theories. So if we're interested in averaging over distinct theories, we also need to mod out by that group, which in this case just turns out to be the integer version of OC comma C. So I claim that this is the moduli space of Narain lattices.
Isn't that thing on the left really ought of lambda naught?
Sorry, it's what of lambda naught?
The automorphism group of lambda naught.
Yeah, I mean, yeah, it's what you, it's if you want, it's the thing. So you can define a lattice by a bunch of generating vectors. I think it's the thing that permutes all those vectors. That's another way of thinking about it, I think. And it's what you call the T-duality group in string compactifications. At least that's what Polchinski
I think it has
called
other elements. I mean, reflections wouldn't be included in permutations, but it's
that's true. That's true. That's true.
I think it's just the automorphism group of lambda naught.
I agree with you, Jeff.
Okay, well, consensus is on your side. I
mean, you're starting from lambda naught, and then you're acting by OCCR, and you're asking what doesn't generate a new lattice when you do that.
That's correct. That's correct.
So anything in OC left or OC right doesn't, and anything that preserves lambda naught doesn't. So you're quotienting by those. And
that's correct.
One X on the right and one X on the left.
That's correct. Yes. Yeah. So it is the automorphisms. Essentially, by definition, that's what I was after, right? It's the ones that give you distinct CFTs.
Yeah. Yeah.
Okay. So now, okay. So this is the moduli space, and there are a couple of different ways of doing the averaging. There's a slick way, and there's maybe less slick way, which was first thought of. I will give the less slick way, I think. But it can be instructive. So what we're after when we average is we want this rho L of delta, which I defined before when I was talking about the partition function. We want rho L of delta of averaged Narain lattices. And in order to think about this, I think it's helpful to first think about a simpler example. So this is something that mathematicians have already done a long time ago. This is due to the work of Siegel and then later Siegel-Way. They managed to show how to do averaging over a variety of lattices. Before considering these Lorentzian lattices, they considered a simpler lattices. So consider, just as an example, a Euclidean lattice in RD. And so these things are generated by, very similar to Narain, they're generated by orbits of, you just take ZD and you consider its orbits under SL2R, sorry, SLDR. So this generates all the lattices. The analogous quotient space that we're integrating over is very similar. It's SLDR modded out by SLDZ. And what you would like to ask is, what is, if I pick some subspace in RD, and I ask on average how many lattice points were in that subspace in RD. So, and what Siegel showed was that that's actually just proportional to the volume of your subregion in RD. So Siegel claims that number of
why is it SL rather than SO? I mean, SL is non-compact. Do you really mean that you're acting with? I mean, I would have thought I'd just take the standard lattice and then I can rotate. Yeah, I'm confused why it's SL.
I guess it's sort of up to you to define the inner product on the lattice, right?
Well, I thought you were just doing a lattice in RD with the standard Euclidean norm. So SL would allow you to like just rescale the lattice. I mean,
But why is that not allowed? Why is it not allowed to rescale to make the length of the vector longer?
yeah, I guess. Okay, I mean, it's sort of the same lattice, but just with a different inner product. But
yeah,
you can rescale
with an inner product. Then I guess it's SL. If it's okay.
So wait, so going back to the case that we were just talking about with the orthogonal group, can we make sure we understand the difference? Why is one the orthogonal group and the other the special linear group?
Well, in the case above, in the OC comma C, the group I chose was the ones that generate different Narain lattices. So Narain lattices needed to have these two properties that I mentioned, and they needed to be unimodular. I think OC comma C is the thing that preserves those two conditions.
I see. It's the unimodularity that's fixing the lengths.
Yeah.
Whereas we're not doing that in the second case.
Okay. So yeah. Okay.
And if you scale, the self-duality would go away, right?
Yeah.
Yes.
Yeah.
In this case, I guess you could consider the orthogonal orbits. That would be perfectly well.
Well, you haven't even told us. I mean, you haven't said it's even or self-dual. So I guess you can.
Well, sorry. Okay. Well, no. Maybe that's I want to consider. I want to consider unimodular. Yeah. Let's do that. That'll fix everything. So I want to consider unimodular lattices in RD.
Oh, but then you're going to have a problem.
Then you need
E has to equal 0 mod 8.
Why? What's the goal here? Are you just looking at some nice subspace of the Narain?
No, I'm looking at a simpler example to demonstrate how to do the counting. Because in general, averaging over the moduli space of Narain lattices, this space is ugly. I don't want to explicitly do the integral. In some cases it's simple, but in general it's ugly.
Well, it's beautiful. I mean, I don't know, it's kind of beautiful. I mean, for C equals 2, for
C equals 2, it's beautiful. For C for C equals 2, it's just two copies of the upper half plane. But for higher than that, like just parametrizing it is a bit of a mess, I think.
All right, but
I could be wrong.
But it's still a very standard mathematical construction where you take a non-compact group and mod out by some maximal compact subgroup and then mod out by some arithmetic subgroup. I mean, it's a very well-studied mathematical kind of object. So.
Right, and well, I guess, what I'm using is part of that mathematical literature, which tells me that you actually don't really need to worry about the explicit form of the thing. There's an easier way of doing these integrals.
Well, and this is a subset of the integral. This is a subset of that problem, right? This is just this is the compactification. This is the just the setting the B field to 0. This is what you get.
Yeah, that's fair. In our paper we only considered OC comma C where C and C were equal. I guess you can do that mod 8, like you can add 8 to one of them, or n times 8 one of them, and you could take that one to be 0. I'm not sure if the duality holds. Maybe it holds. Maybe I'm not sure.
This is the space of deformations of the metrics on a torus. Right, SLDR mod SLDZ.
Yeah. I'm setting. Yeah, that's like it's like what you said earlier. I guess you're setting C bar to 0.
No, I'm just saying, what's the space of metrics on a torus?
Sorry, are you talking about? You're talking about this example, this thing here?
Yes.
Yeah. So why are you saying this is a subset of Narain lattices?
Because the space of Narain lattice is the space of metrics plus B fields. This is just the space of metrics.
But it can't be, okay, no, fair enough, but it can't be with C and C bar equal, right? Because it's not, can you embed this into this?
Yes.
I mean, yeah, because just, you know, that space also parameterizes inequivalent G and B fields. So if you just set B to 0 and want to parameterize inequivalent G fields with B equals 0, that has to be a subspace.
I see. Okay, fair enough. Fair enough. I just don't know how to think about it in terms of the lattice, I guess.
If you impose unimodularity, won't this just like do the thing on the one part of it, like the X, let's say, and not the Y?
Well, that's not allowed, right? Because you still need x squared minus y squared to be an integer. Yeah, so that's a bit confusing to me, right? So I don't know how to preserve the integrality of x squared minus y squared by acting with just SLDR mod SLDZ. Unless
SLDZ is just the it's just the basis changes of the lattice vectors.
no, yeah, I understand. What I'm saying is, sorry, I think I'm frozen. There we go, we're back. What I'm saying is that the action of this SLDR on SLDZ, I don't know how it acts on delta and L, which in the Narain lattice were x squared plus y squared and x squared minus y squared. I agree with you, since it's just you know, keeping the B field fixed and just doing the integrals over G, it should correspond to something. I just don't know what that is. It's not a straightforward math, that's all.
It doesn't, I think it doesn't do anything.
I think it rescales this, but it doesn't touch this. But I could be wrong.
Yeah.
Right. Okay, so I mean, yeah.
I'm a little bit confused about this the group that we are using. I mean, so SLDC, shouldn't it be something like SOD?
Not if I guess I'm trying to keep it unimodular. Maybe this caused more confusion than it was supposed to resolve. I was just trying to give a simpler example than the Narain lattice by considering just Euclidean unimodular lattices, which are basically their definition is the lattices that are generated by the action of SLDR on just the integer lattice. And what I wanted to argue was, well, if I wanted to count the number of lattice points in some subregion A, so I wanted to say that the number of points in some region A, which is in RD, I wanted to say is proportional to the volume of A in RD. This was just supposed to be an example before I went to the Narain, but maybe I'm not being super clear.
Well, I think the problem is, so the space of metrics, I mean, a metric is a D by D symmetric invertible matrix, right?
Mm-hmm.
So that has D times D plus 1 over 2, I guess minus 1 for the invertible condition parameters.
Mm-hmm.
But SLD, doesn't that have dimension d squared minus 1? Because it's just d by d matrices with determinant 1.
Unit determinant, yeah.
Yeah, so the dimensions don't even match.
So maybe it's not the space of metrics on a torus then?
I don't think it is. I think this SLDR is not right.
Well, it's SLD, the space of metrics on a torus is SLDR over OD.
Okay, that I can believe. But OD is a maximal compact subgroup of SLD, right?
That's right.
Yeah, so, okay, you need to quotient by that. So in your, I think you need a quotient on the, well, if you want to do by SLDZ on the right, then on the left, there should be a quotient by OD probably.
Yeah, but I'm just stating that the SLDR mod SLDZ has nothing to do explicitly with the Narain lattice. It's just a mathematical question, which has nothing to do with CFTs or anything. The question is, how do you count the number of points on average?
But I think that's what we're talking about.
I thought you were saying that you were trying to fit the SOD.
No, look, all Emil's saying is that the space of metrics, which should be this moduli space that you're talking about, requires a quotient by OD as well.
Are we talking about here? Are we talking about this one?
No. In this,
this one.
Euclidean metrics, your formula where you are SLDR mod SLDZ, all Emil's saying is that there should be a quotient on the left there by OD.
ODR, yeah.
ODR. It's still a double coset space.
Sorry, but Nima, are you making any claim about this being a space of metrics, or is this just a space that you're?
No.
Yeah.
Okay, so.
But the question remains. I don't know if for the mathematical statement that I'm about to make, for the counting, you need that quotient. I need to look that up. It's not obvious to me. Because everything that I'm saying doesn't really have anything, it doesn't really take input from the fact that this is the moduli space of metrics on a torus. It could be, I'm not sure. So I'll put a question mark here and I'll look that up and I'll let you know.
Okay, I mean, it just, probably neither here nor there. It just, it gives your example some context.
I see. Okay, well, some subgroup of this has the interpretation of being the space of metrics on a lattice. But from my perspective, I guess all I want to do is just get a sense of how to do the counting of, if I give you some subregion in RD and I average over these lattices with the orbit that I define, what is the number of lattice points that I'll find in that region? And Siegel claimed that it's proportional to the volume. And to prove this rigorously, it's a bit of a handful. Obviously, I'm also talking about the case where D is greater than 1. But you can heuristically argue for this, and maybe let me give a heuristic argument. So if you define a measure mu on RD such that mu of A is counting the number of points in A, well, I know by definition that this mu has to be invariant under SLDR. And I know that this SLDR acts transitively and it preserves the volume form. So that sort of tells you that you can write down an ansatz for what mu has to be. It has to be proportional to the volume form, where this is some arbitrary constant. But on top of that, the one point that I swept under the rug is the fact that all of these lattices have a point at the origin. Every single one of them does. So I'm going to include that explicitly with some unknown coefficients alpha and beta. Now the question is, how do you fix alpha and beta? Well, alpha is kind of easy because every lattice has a single one. So that sets alpha to be 1 when I fix my normalization. Beta. Beta is also relatively easy to fix if you consider you take A to be very large. You take it to going to infinity. The fact that these are unimodular lattices and SLDR preserves volumes tells you that within every unit volume, there will be roughly 1 lattice point at a given instantiation. So that tells you that beta itself has to be 1. Now, the reason I'm mentioning the simpler version is because for the Narain lattice, what we do is almost identical. You can write down an ansatz with unknown coefficients and then fix the coefficients. That's why I wanted to mention the simpler example before I go to the Narain lattice case. Is that okay? Is there questions about that? At least the logic of what was happening there. So I'm interested in counting the number of lattice points after averaging. And now I'm going to apply what I said above for the simple Euclidean lattice to the Narain lattice. So, okay. Now for the Narain lattice, it's very similar. So what I want is mu on A, which is invariant under OC comma CR. But I don't want it on the entire space. I want it on the hyperboloid, which is defined by the spin condition, which is that x squared minus y squared equals L. Because the states are constrained to move on these integer defined hyperboloids. Now, again, it's very easy to argue that this thing has to be proportional to the volume form on the hyperboloids. So all you need to do is work out what the volume form is on the hyperboloid, you parameterize it. Let me not go through that exercise. The claim is that once you parameterize it and you compute it, the volume form, what you find is that this dx squared minus dy squared is going to be proportional to delta squared minus L squared to the C half minus 1. So the claim now is that mu, again, is going to be proportional to this volume form and some delta function at the origin. And the question is, how do you fix the coefficients? In the previous case, there was just 2 coefficients. In this case, there's infinitely many coefficients, 1 for each L that I need to fix. And the way you fix them is you do some asymptotic analysis. Essentially, I don't find it's a problem in math. It's a counting problem in math, which I don't really find very instructive to go through in detail. But let me just tell you the result of this counting procedure. The result of the counting procedure is that you can write down this density of states rho. It is going to be proportional to this volume form that I wrote. And in the case where the spin is 0, so for scalars, it has that delta function that I talked about. These are those unknown coefficients that we had to fix using analytic number theory and just doing the counting problem explicitly. So I have an explicit expression for the density of states here by essentially doing the counting. Is there any questions about that?
Yeah, I know you don't want to get into the details, but in that formula, are things what we expect? So zeta is the zeta function, gamma.
Yes, zeta is the zeta function, gamma is the gamma function, and the sigma is
the divisor function.
Yeah, it's the sum of all m to the 1 minus c for all positive integers that divide L.
Okay.
Yeah. So there's some explicit calculation you can do. It's essentially application of Hardy-Littlewood circle method to some explicit expression that counts the number of vectors. You just approximate this integral It's kind of a fun calculation, actually.
Nima, can I ask how much longer do you have in this talk? Because the details would be interesting to hear.
Well, let's see. I wanted to give a short aside as to how this came about. And then the last thing I was going to mention was a couple of slides on the holographic dual. I mean, I'm already kind of over, aren't I? So I'm happy to talk about the details if you want afterwards, or I can just stop and talk about them now. It depends how people are feeling.
I mean, I would be happy to go for a while, but
okay, how about this? How about I finish the main points, but I'll stick around and we can talk about all sorts of things.
Okay.
All right. Okay, so maybe just let me briefly mention a short aside as to how we came to calculate these things. We were interested when we started working with Henry Cohn on sphere packing, which is very similar to the problem of modular bootstrap. So in modular bootstrap, you're interested in computing the spectral gap. And in sphere packing, you're trying to find the highest density of packing balls in some d-dimensional space. There's an equivalent between these two problems, which is talked about explicitly and nicely in that paper. But in both cases, this is difficult to do at large C, or in sphere packing, C is the dimension of the space in which you're trying to do the sphere packing. So it's difficult to even numerically know what the spectral gap is at large central charge. However, you can do the averaging. And when you do the averaging, what you'll find is that the average CFT will have a gap that scales with C as you take C to infinity. And this smelled very much like a theory with holographic dual in the light of what I was talking about pure gravity. So the gap that we found isn't C over 12, but it's C over 2 pi E. So this sort of made us think that there might be a holographic dual to this situation, which is what made us explore this.
Are these, sorry, with this gap, are these like Virasoro primaries or primaries of the U1 cross
They're
U1?
primaries of U1, the U1 cross U1, yeah. But the mapping between the two is pretty simple. The U1 to the C times U1 to the C characters you can write in terms of the Virasoro characters. It's just the eta functions. You just want to distribute the eta functions.
Sorry.
Yeah.
Delta 1 is what?
Delta 1 is the scaling dimension of the first primary operator above the vacuum.
But before averaging, there were plenty of operators with dimensions that were much smaller than C.
That's correct. And I claim when you take C to infinity, the fact that the degeneracies have to be integers forces, there's an exponential fall off if you, in the number of possible operators with scaling dimensions less than and above. It becomes like a step function, that degeneracy. It goes from 0 to something exponentially growing. So what I claim is that if you take average large C Narain CFTs, the majority of those terms in the ensemble will have first primary operators, they're delta 1 of order C.
But that's what I'm confused about. So if I just take some generic Narain lattice and I ask, what's the light spectrum? Well, the biggest gap I can make is when the lattice is self-dual, and then the gaps are order 1. And if you go away from self-dual lattices, right? So it's like, if I have just a circle, right? The biggest gap I can make is when the circle is the self-dual radius, and then the gap is order 1. And if I make the radius much bigger than, you know, the string scale, then there are a set of momentum modes which just get lighter and lighter. So I don't see how taking a spectrum which has oodles of operators whose conformal dimensions are small, and then by averaging somehow those small dimension operators are just going to go away.
Sorry, why is it obvious to you that when C is large, you're going to have an easy time constructing short vectors? That's, yeah, why is that obvious? In fact, this is a hard problem in math.
So set all of the momenta except one of them equal to 0. Right, just take a vector which is 0, 1, 0, 0, 0, 0, 0.
And the scaling dimension of that, I guess, will be 1 over the momentum in the shortest, or 1 over the radius of the shortest, or 1 over the radius of the vector that you chose. Yeah,
that's right. So
yeah.
it never exceeds 1.
Why does it not exceed 1? How do you know that the shortest?
The radius is always bigger than 1.
Sorry, why is the radius always bigger than
1? Because the ODDZ cuts off the moduli space at 1. I always do I can always make do a T duality so that the radius is bigger than 1, and consider momentum modes on that torus. And so the lightest operators will always be of dimension bigger than, smaller than a quarter, I think, basically. Self-dual radius, the lightest operator's dimension a quarter.
The question, sorry, okay, fair enough. The question is, once you do the averaging, if you draw randomly from this ensemble that you averaged over, what is the typical lightest scaling dimension operator?
Right, so if I take a bunch of theories, all of which have spectra lighter than a quarter, and I do an average, then the worst I could get is that the lightest operator has dimension a quarter.
I think I disagree with you that they all have operators with scaling dimension lighter than a quarter. Why do I say that? So scaling dimension is 1/2 x squared plus y squared.
Is this going to be one of those screwy properties of high dimensions?
Yeah, I think Emil, he's saying that there are very few such things, right?
What's that?
There are very few. I mean, for example, if you take the lattice to be a product of C circles, and C is a trillion. So, of course, what you say is true for each of the circles, but if you ask how many states of the sort you're talking about there are, and on the other hand, how many states there are with a very large dimension, the number increases very rapidly with the dimension, right? When C is large.
Okay, so but then I'm not computing then a partition function. I'm computing some kind of partition function where I've divided by some large number.
I mean, this lower bound is, I think what he's saying is that the number of states, take this problem of a trillion circles with some random radii of order 1. So the number of states at a given level goes very rapidly down, when the level goes.
This must be hiding what I think is kind of the issue here, which is that if I'm counting states, I get a sum of a bunch of delta functions, and the coefficients of those delta functions are integers. So that's okay, fine. And now I do some averaging. I think what you're saying is that those delta functions. So my claim is that there's a delta function always for dimension less than a quarter. And it sounds like what you're telling me is that, well, what I really need to think about is how sparse are those states? And what you're telling me is that when I do the averaging, those states all go away because they're sufficiently sparse.
I think, yeah.
It's not that there are it's not that there aren't any very light states for any individual lattice. It's like you're in the process of averaging to make this continuum. The sort of like average density is going to zero.
I think that's correct. I think you should take my statement in this. The precise form of my statement is that the expected number of primary states below, with scaling dimension below 1 over or c over 2 pi e goes to 0.
Wait, but I thought it didn't go to 0. Sorry.
Below 2 pi, yes, it does. Sorry, the expected number of operators.
No, but Emil just showed us that the expected number is 1, at least.
It can be of order 1. It doesn't scale with c. That's fine.
I see. So it counts as 0 if it doesn't scale at least as fast as c. Is that the?
Yes. I mean the only statement. I mean the proof of the statement is 2-line. I can show you what it is. It's just you.
No, I think it's not a question about the proof. It's just a question about what it is that is being computed.
I understand. I was just saying the proof is not about whether or not you have operators below this gap. It's about the expectation number of operators below this gap. If you choose a random theory out of this ensemble and you look at its spectrum. Sorry, no.
No, it's that divided by.
Yeah, that's right. It's that divided by that's correct, by the total number of, just normalize the ensemble. Yeah.
But I'm confused. Like if I say, if I ask the following question. So let me take the spectrum. I proved to you there's an operator of dimension less than 1/4. So let me take the density of states and integrate it for all conformal weights less than 1/4. I'll get a number which is always bigger than 1. And so if I average that number over your ensemble, I'll get a number which is bigger than 1. So there must be some game being played about when you're doing this average, you're converting a discrete spectrum into a continuum, and then you're watching the normalization of the continuum go to 0. But yet there are still, a finite number of states there. So it sounds like the question is, the answer, it sort of depends on what question you ask.
Right. I think the precise statement I guess I want to make is that if you take an integral over the density of states with this rho that we computed above, and you ask how many of these operators are below some number proportional to c. So there's a unitarity bound. So the spectra are from L to some parameter that I define here. And you just try to count them. You will see that this thing is at most proportional to, it's at most when you take c large, pi alpha c to the c over some number, it doesn't matter, some gamma function of c half squared, which we can show using Stirling formula is just 2 pi e alpha. Now as you take, to the c, plus order 1 to the c. Now I claim that as c goes to infinity, if this alpha is less than 1 over 2 pi e, the expected number tends to 0 as c goes to infinity. But the additional thing that I'm using here is that that the number has to be an integer. So maybe what I want to claim is that most of these CFTs that you're saying that have a light operator, maybe the degeneracy is 0. Is that a possible way out?
I don't think so.
No, it sounds like every single element of the ensemble has such a light operator.
Hmm.
What is the row? How did you make row? Is row
Row?
discrete, or is row already some kind of continuous?
This is row. The row is the density of states for the average Narain lattice.
But its definition was in that earlier equation where you wrote Z as a sum over L and an integral over delta, right? I mean, you had a formula for Z in terms of row.
For Z, yeah, that's right. Yeah, it really should be interpreted in an integrated sense. That's correct.
So the spectrum has already become continuous.
So you have to integrate over delta, right?
That's right. That's right. I can't really make statements about row itself. Only statements about integrated row make sense.
But I guess the question is, how did you take this? How did you get this continuous row from the discrete spectrum?
I took it by explicitly averaging over Narain lattices.
But in that averaging, do you count degeneracies in a finite window that are smaller than C as 0?
Yeah. Count this formula is exact in C. Yeah.
So Nima, would it be safe? I mean, if you go back to that formula for Z in terms of row.
Yeah.
So should I think that what you're doing is you're integrating Z with some measure and then using that to define some like row effective? I mean, this row L of delta is, if you're given a particular CFT, there's a particular row L of delta.
That's correct, yeah.
But now you're defining some kind of averaged row L of delta?
Yeah, that's correct. So in principle for individual CFTs.
I mean, it might be nice to have a formula for what the thing you computed is actually given by. I mean, it's presumably involves some average of this Z.
That's correct.
And then projected onto a particular L.
So, you agree that for individual CFTs, this is a sum on delta functions of delta minus delta I, sum on I with some density rho I.
Right.
But at the level of the integral, I think I'm allowed to, especially once I do the averaging, I'm allowed to talk about rho as a continuous function, which under the integral will give the same answer, like after I do the integration.
All of this is fine. We're just trying to understand where you did some division so that you can avoid Emil's problem.
Yeah, I understand.
It sounds like you're saying, are you saying that if the number of states in a window is less than order C, it somehow counts as 0? Like, is there a large C limit somewhere in this problem?
Yes. I mean, yes, I've explicitly said that. So what I claim is that.
But how does the large C limit affect rho, the thing that you call rho?
Well, it explicitly, I guess, depends on C. And what I've written here is the number of states. Yeah, that's a good point.
Like, do you somehow normalize rho by C in order
to get
a limit?
Wait, I don't think there's actually an issue here if I'm just saying that I think what Emil is saying is correct, that there is order 1 number of states with scaling dimension less than this funny value, whatever it is, this thing.
So one thing that's true of very large dimensions is that all of the states that I'm talking about are kind of living along the lattice vector basis vectors. So in other words, if I picked a lattice vector sort of generic lattice vector, all of whose entries are of order 1, then that would have a dimension of order C. But
That's
if I
correct.
pick lattice vectors, almost all of whose entries are 0, then those are the guys who are dimension of order 1.
That's correct. So I think the claim that I'm making is not incompatible with that. All I'm saying is that if you look at the degeneracies, the ones that are of degeneracy order C will typically, the ones that are dense that there will be lots of, they will have scaling dimensions of order C. I think the ones that you say exist, and maybe they exist in all CFTs based on what you said, like every lattice will have an operator with some small scaling dimension, but I claim that they don't grow with C. As I take C large, you're much more likely to have operators with scaling dimensions above
completely
this.
agree with you. The number of them will be, well, let's see, it won't be necessarily order 1. There will be of order C of them, because, right, I can pick them to be, then I have my choice of which basis vector they point along. The thing they won't grow like is C to the C.
That's, let's see. Sorry, you're saying the degeneracy is over order C, but it's not C to the C.
Right, that's what you got. You got C to the C, if I'm looking at your spike, correct?
That's correct. That's correct, yeah.
And the ones that I'm counting, I think there are of order C of them.
Because there's C such vectors out of which you can set all the other ones to 0.
Yeah.
Yeah, I think that's correct.
Or at best, it's like C to a power, maybe exponential in C, but not C to the C. Well, in fact, we kind of know what they are, right? So I'm looking at things that have momentum, they're light momentum modes. So they should be growing like the density of states of a massless gas in C dimensions. So it's like they should be exponential in C, but not like C to the C.
Right, there should be like delta to the C or something like that.
Yeah, it's just momentum modes on a very high dimensional torus. So they should grow like a massless gas in C dimensions.
Yeah, okay. Fair enough. Okay. So does that resolve this confusion that it caused?
I think it's okay.
Okay. Let me just quickly go through the gravity thing, and then we can come back and talk about other things if you guys are interested. Okay, so the statement of the holographic dual is the following. By the way, I should say all these things that I'm deriving can be derived another way using the differential equations that these objects satisfy, which we can talk about that also if people are interested after. So I make the following claim that this thing is dual to what I call U1 gravity. And I'll tell you what that is. This is described by some Trent-Simons action, summon I from 1 to C of a bunch of gauge fields. And in the definition of the theory, I also take plus sum on topologies. This is part of the definition of the theory for me. And it is chosen not for any deep reason, just that I want to get the correct answer. So for the torus boundary, the sum on topologies is essentially the same topologies that Maloney and Witten summed over when they were doing the Poincare sum. In other words, they're the the different ways of filling in the torus. Just different contractible cycles. Different, let me just not write that down. Different VTZ topologies if you want. I should say for the torus, this choice is not much of a choice. Those are the only ways of filling in the torus. But for higher genus partition functions, these aren't the only ways to fill in the torus. However, the duality that Witten and Maloney showed is the duality which is not all possible ways of filling in the torus, which is what you would expect from a decent theory of quantum gravity, or that's what I would expect. You should sum over all possible ways. But this theory, which is some very basic free theory, is dual to very particular ways of filling in the boundaries. So that's just a side comment. So you can pick one particular way of filling in the boundary. So for example, you can take the thermal ADS and compute explicitly the path integral with a torus boundary. In fact, this was already done by Witten, by Parati, by various people. And what you find is essentially just a vacuum contribution of U1 to the C times U1 to the C characters, if you want. And I should say that this is the full answer because the theory we started with was free. So this is the one loop exact answer. There's no corrections to this. After all, we were dealing with a free theory, so we should be able to compute it. Now, to get the full partition function, what you're supposed to do is sum on topologies of this thing that you just computed, which in our case, let me write it down explicitly once, just summing over SL2Z mod Z of essentially 1 over eta gamma tau to the C. This is something you can do explicitly, but first maybe let me write it down in a different way. Let me just write it down like this. Eta to the minus 2C times some sum over the same gamma, blah, 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 times m gamma tau to the C half. I just use the fact that this combination is modular invariant to pull it out. And this thing here is some object that's known to mathematicians. It's called the real analytic Eisenstein series. It's not the ordinary Eisenstein series we're used to. It's a little different. Those are holomorphic. This is their cousin, which is still a nice friendly object which satisfies some nice transformation properties and so on. But we'll not talk about it. So here's an explicit partition function we computed by doing this path integral and doing some sum over topologies. Now it's a trivial exercise to compute rho of delta and L. I will not do it. You do the Fourier transform to project onto a spin, and then you do the Laplace transform. You can do this explicitly, and what you will find is exact matching to what we computed before. Match with average CFT. Let me just quickly make some comments about what this thing even is, this holographic dual. Why do I even call it gravity? So this thing is, some comments. This is not Einstein gravity. It doesn't have the simple Einstein-Hilbert action, obviously. But it does have gravitons. So it has gravitons, which are, from the boundary perspective, these things are composites, in the sense that on the dual, you construct the Virasoro out of the modes of the stress tensor, which is essentially, it's a Sugawara type construction out of the U1 to the C times U1 to the C currents. And on top of that, it has saddles that have geometric interpretations. So it's not completely crazy. I will iterate again that the choice over, this was a provisional choice. I had no good reason for them other than the fact that this worked. I should also say that this holds at higher genus, as I mentioned before, and it also holds for disconnected boundaries. So things like these geometries, some calculations along these lines have been done by Maloney and Witten. And
Nima?
Yeah.
I think like a week or so after your paper, there was another paper that seemed to claim that that I wanted to know if it's the same holographic dual as what you're saying. It said that it was like Einstein gravity with like U to the D1 gauge fields. Is that like fundamentally different or just some sort of rewriting? I don't know if you know what paper I'm talking about.
People, so there was some South American people, right?
I think so.
I think, yeah. I didn't read their paper in detail. They said that if you instead consider some metric with some funny boundary conditions, you get the thing that's dual to this. So instead of talking about the Chern-Simons, they wrote some gravity action, but with some funny conditions imposed on the phase space. I didn't read that paper. I can't tell you in detail.
Okay, so may or may not be different. Yeah.
I think it is the same. I think they just gave a different interpretation of the bulk dual in terms of the metric, but with some funny conditions imposed on the phase space. Right. So yeah, with that, okay. So let me just, since I've already gone so far, let me just flash some Outlook and questions, and then we can talk about other things. So maybe so we found an explicit instantiation of this, some theory of gravity with including some over topologies being dual to some average over CFTs, which is one other example other than JT gravity, and it's in one higher dimensions. There's some obvious questions you might want to ask. Is there other ensembles for which this works? Is there operators on Wilson lines you can ask? Can you compute the spectral form factor and see things like the plateau ramp and so on out of this type of a construction, if you're familiar with that story? And is there some general lessons that we need to take away? Does this type of thinking, this line of thinking, help you understand the factorization problem? Whether we should take those other saddles that connect disconnected boundaries seriously, or are they just accidental thing that seem to be helping get the page curve and so on? Another question is, do these things have more standard interpretations? The talk I saw at Strings by Comran claiming that JT gravity can have an interpretation in terms of Wilson line expectation values in ordinary string theory, which I didn't understand, but maybe you guys would know more about this and could tell me about it. Maybe these things are some M2 brain expectation values or something. And let me just stop there, and we can talk about other things if you guys are interested in talking about it. Thanks.
And Nima, can I ask about the spectral form factor?
Yeah.
So you probably don't expect in your theory to get the ramp and plateau stuff. You're saying maybe in other versions.
Why do I not expect it in my theory?
I mean, it's not chaotic. You don't have
it should still have the plateau though.
Yeah. You don't have eigenvalue repulsion.
That's true. I can still have the ramp, right? I mean, I agree.
You'd still have the plateau. You probably wouldn't have a linear ramp. The plateau is just the discreteness of the spectrum of each individual theory. So you'll still have there's no reason to have a linear ramp though.
Right. I think if you have Poisson statistics and, I don't think you'll have the full ramp.
But the plateau is just
Yeah, if your
is
spectrum
the
is discrete.
important thing, I guess. Yeah.
Sorry, the scaling dimensions of individual instances don't have Poisson statistics, right? If you pick a large C random lattice, I don't think these things have Poisson statistics. They might. I might be wrong.
Unless you put it in. I mean, it depends how your randomness. But the spectrum of any instantiation, any of your lattices is probably. Well, okay, maybe some of your lattices look random in the sense that the relative. I guess you could put the randomness in to kind of, but the spectrum probably won't want to look very random, right?
Yeah, okay, fair enough. Maybe you don't have the same features. You might have some features. Either way, I guess it's worth studying to see. Some contributions to this have already been computed in this paper of Witten and Maloney, but not the whole thing. There's still room to do this calculation explicitly and check.
Hey, Nima, can I ask a question about your formula involving this kind of Poincare sum with 1 over eta squared?
Yes, please.
So I'm more familiar with formulas like that in the holomorphic context where you're averaging some, something that's just a function of tau. But there you need to have something that has weight 4 or greater in order for that sum to be convergent. Is this sum actually convergent somehow because you have both eta and eta bar, or do you have to regularize it?
For C greater than 2, it's just convergent.
Oh, that's to the C down there. Okay, gotcha.
Yeah, so for C greater than 2, it's convergent. For C approaching 2, I think you can make sense of it still. There will be some excess of operators in the scalars. There's some weird singularity thing that happens, which I think you might still be able to make sense of.
It's probably like the, if you try to average something weight 2 that's holomorphic, then you get the non-holomorphic Eisenstein series, E2, with that non-holomorphic part. If you try to regularize it in a way that preserves modular invariance, then you get that non-holomorphic part.
Yeah, there might be something like that where there's some anomalous piece that breaks modular invariance as you try to take C to 2. I think you're right. I haven't tried to explicitly check it, although C equals 2 is kind of interesting. One, for the reason that you said, which is that, the moduli space in that case is just 2 copies of the torus moduli. Right. So altogether, you have a partition function which depends on 3 moduli, the worldsheet moduli and the moduli space moduli. So, and the function is invariant under swapping permutations of these things. So in some sense, the averaging over the moduli space can be replaced by averaging over the worldsheet moduli space, which is something I'm a little more comfortable doing, I guess. But is this part of a more general thing where averaging over couplings in quantum theories can be replaced by time averaging or something more sensible, which I'm more comfortable with?
You think there's, another interesting example where at least the moduli spaces know it exactly is K3 conformal field theories. You couldn't, I guess you could take a large C limit by considering the symmetric product, but even for a single K3, you have this SO20, 4 mod, blah, 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 double coset. Is there any chance of figuring out how to average over that?
You'd have to find something to compute that explicitly that depends on the couplings, right?
Yeah.
Right. I guess the partition function is the simplest thing I can think of.
Right, but that's surely not known explicitly.
Yeah, you don't know the partition function.
I wonder is there BPS spectrum or anything like that that's known explicitly?
Oh, but that doesn't depend on the moduli.
That's true.
Yeah.
Okay, so
makes it easy to average.
Yeah.
Well, I guess, yeah, okay. Yeah, either the average is easy or impossible.
There might be some intermediate examples, like, for instance, I think there are some correlation functions in K3 whose coupling dependence is not 0 is not trivial, but fixed. Like kind of extremal correlation functions with like a bunch of BPS and then some one anti-BPS.
But you think they depend on the moduli?
I think so. They probably do.
Is the metric known on the moduli space?
Yeah.
Yeah. It's a symmetric, it's a Narain type.
Yeah, it's a Narain.
I mean, there's
I
it's the Haar measure, right, on these groups, and so
Yeah,
that's
yeah.
inherited by the quotient. So
I see. So the same thing is here, basically.
Yeah, that seems like it would give a real test because those things probably really are very complicated spectrum and so forth.
yeah, it would be cool to find a generalization that was a little more structure.
But for this, you don't need to talk about K3. You can just replace it by the heterotic thing, right? The 4,20, gamma 4,20.
Yeah, but yeah, again, yeah.
I
right.
want something interacting. Yeah.
But you want, yeah, I guess you want something.
I mean, it's the same moduli space by S duality, right?
Yeah, that's true. That's true.
By the way, I have a stupid question. So you talked about this U1 to the D cross U1 to the D Chern-Simons. So there's some story from 30 years ago that, also by Witten, I think, that even for D equal 1, so if you do U1 cross U1, that's the same as just, in your language, a C equal 1 on a given lattice, gamma 1, 1. So you have to be careful about what you do with the zero modes, but that's the whole point of the kind of old Chern-Simons CFT duality. So, so you know, and you can of course do it for any U1 to the D cross U1 to the D. In other words, like you can do this game of U1 to the D cross U1 to the D Chern-Simons versus a CFT for any value of the moduli. And then if you want, you can average on both sides, but like I don't understand in what sense.
I think
you know, the relation between that story from 30 years ago and what you said is not clear to me.
I think what I saw, you can correct me if I'm wrong, but I think the story from 30 years ago was you take the Chern-Simons action and you sum over all possible flat connections at a fixed topology. Whereas here, I guess I'm not really doing that. I'm just fixing the trivial connection. So I'm setting essentially A's to 0, and I'm computing just a one loop determinant path integral around that background. So when I write this thing down here, that's what I'm writing down.
No, that part is also in the story from 30 years ago.
Oh, there is. But I thought you'd also have to sum over non-trivial.
No, of course. But like what I'm saying is, of course, part of the 30-year-old Chern-Simons CFT duality is getting the 1 over eta absolute value squared for U1 left cross U1 right. But in that case, you also have to think about how to treat the zero modes of this gauge field to get the Narain thing for the P left and P right on the boundary. So I guess, you know, so I don't remember the story from 30 years ago very well, but it must be that whatever it is that you're doing here, so certainly this one loop of fluctuations around whatever, that is not different between the story from 30 years ago and what say Porati and company talk about. The difference is definitely not there. The difference is in how do you treat the zero modes. I don't know if anybody here.
I don't know if it's the zero mode. It's more like the action at the top of the slide can be generalized to you know, instead of being diagonal, it's just some general quadratic form.
Yeah, but
and
that's
not, over and what you're doing is averaging over that quadratic form.
No, but like, see, just like so both in the two-dimensional example and, sorry, the description, and in the three-dimensional description, there are two parts to it. One is, but basically in in the two-dimensional description also, you can say my action is dxi d bar xj times some gij, and the scalars xi all have periodicity 2 pi, which I think is what you're saying. I'm not talking about the gij in front of the action. I'm talking about the identification, like the three-dimensional analog of the identification of xi with xi plus 2 pi, okay?
Oh, isn't that just a question of whether your group is U1 or R?
Well, yeah, but like, so the story from 30 years ago is you do the, yes, but in what we just heard, that becomes, so yes, so you take the group U1 to the D cross U1 to, U1 to the D, you put what you said, like the gij in front of the kinetic terms, and that gives you one realization of a Narain lattice on the boundary, right?
Yeah, actually, I think maybe it's might be a little different than that. So you also need to incorporate a boundary term. And
yeah, of course, yeah.
And that's where you couple the A's and the A tildes.
Yeah, no, I mean, look, there are some details, but those details are details of that 30-year-old story. Now, what I want to know, so now, you know, that 30-year-old story, so of course, yeah, so say, I think in the Porati paper, they write those boundary terms. But
and
again,
that's where the quadratic form appears, because that's the only thing that couples the A's and the A tildes.
Yeah, so that all goes back to that story, but that gives you one realization of, in the language of this Narain, etc.
Yep.
Now, and then the question is, so you take, now again, this is all 30 years old. Now you say, okay, so you know, so that story is the path integral of the Chern-Simons with all the things you said is the same as the boundary path integral over the CFT with a given set of Narain moduli. So now the question is, you take that equality and you integrate both sides over the gij and the bij, right? And the question is, you know, so on the right-hand side, the two-dimensional description, it's what we just heard. On the left-hand side, you have to tell me how that old story from 30 years ago becomes this story. And certainly the small fluctuation, you know, the quadratic Gaussian fluctuations around the A equals 0, they're, you know, they're, for example, obviously independent of the moduli, okay? Like this 1 over eta absolute.
Yeah, sure.
So that's definitely not the issue, right? It's something else here. That's my question, basically. How do you go from that to this on the Chern-Simons side? So did anybody do this or no?
I don't think so. I mean, you would expect Witten, since he wrote the original story, would talk about this explicitly, but
he doesn't.
Not as far as I know. I thought the 30-year-old story was slightly different in the way the Chern-Simons theory was defined. I thought it had some additional thing going on, which was giving you a particular instance of the Narain lattice. To get a particular instance of the Narain lattice, you had to do something extra, I thought, but I could be wrong. Whereas
what was the something extra?
Like I said, I'm not, I don't know the details, but I thought was some additional configurations that you had to sum over or something along those lines, which we're not doing here. It was the old story that you take the Chern-Simons action, expand around the trivial gauge connection, and then just do the path integral. So how's that different than this current story? I thought there was some difference.
A lot of the old story was kind of unpleasant because they took just, in your language, the A without the A tilde, and then they were standing on their head to talk about the chiral scalar that you get on the boundary. And of course, this is not the greatest theory that God invented, the single chiral scalar. But I mean, I think, look, I don't remember to what extent, I never worked on it myself, but I mean, of course, I mean, basically, I'm surprised by the statement that you can take this action and do the path integral, you know, the same gauge group, the same action with the same boundary terms, and do two completely different path integrals. One that usually that doesn't happen, right? In Q. In QFT, once you specified the action and the manifold on which you're doing the path integral, it's not like you can do whatever you want. You know? So that's essentially my question. Okay, if nobody thought about it, it's fine. It's not.
Yeah, no, I personally haven't, and but I agree. If there's a particular Chern-Simons that's dual to a particular instance, what happens when you do the averaging on the other side? I don't know, and that might give some insight as to what the hell is happening here, because it's still kind of mysterious to me why this is happening.
Mm-hmm.
Is there other questions? I'm happy to talk about this offline or online right now, whatever you guys want.
I don't know.
Thanks
We're
for talking.
past 2 hours now.
Yeah, I think I'm out.
Okay, yeah. You can take a break, take some rest, and feel free to message me.
Very nice talking to you, Nima.
Thanks, Nima.
You're welcome.
Thanks, Nima. You should probably stop the recording, I think.
Good point.
It's gonna be a big file.